All right, so we're looking at page 2 of exam 3 for the spring 2019 semester. And this is more fill in the blank, although now we're getting into a little bit more, let's maybe say, technical questions. So more than just the standard fill in the blank, maybe a little bit more thinking here. Now this first one here, I caught a lot of you guys with this. I didn't want it to be this tricky, and we had talked about this in class over and over and over, so I know you can't see it, but imagine me wagging my fingers at you through the screen here, okay? So again, take a look at what we have. We've got an ester, right? We've got an aryl halide. We've got a carboxylic acid, and that should be big red flag. So there's my red flag. Okay. All right. All right. There's that. We've got a Grignard. We've got an alkene, right? We've got an ether over here, and we're just mixing these two together, right? So the aryl, under these conditions, we're not really going to do anything to the aryl halide, right? The alkene isn't probably going to do anything, and it doesn't look like our ether is really going to do much in this case also. Which leaves our Grignard here, right? Which leaves our Grignard, which what do we know about Grignards? Well, they're extremely powerful bases, right? Extremely powerful bases. And extremely powerful bases like to look for what? Well, they like to look for acids. Do we have any acids around? The answer is yes. Okay, yes we do. Right? So what's going to happen in this case is just a simple acid-base reaction, right? We were in the lab. We wanted to couple together our Grignard and our other compound, right? We wanted to bring these two compounds together, but we weren't paying attention and we had an incompatible functional group, right? So the answer for this is all we're going to do is a really fancy acid-base reaction where we deprotonate our carboxylic acid and we protonate our Grignard there, right? Not really all that useful for us, right? So our answer is going to be this, right? We just leave everything else intact, right? And we just end up making our carboxylate, and we just unfortunately end up protonating this guy here, right? So if we want to add some color, let's say that guy right there ends up right here, right? We just do a simple acid-base reaction, right? Well, that's not that interesting, right? Why, I remember what I said about carboxylic acids, right? The first thing we have to pay attention to is that they are acids, right? They are acids. And they are going to react like acids, right? If we've got a strong base around and we've got in organic terms, carboxylic acids are strong acids, right? Not in general terms, right? But for what we care about. They're strong acids, so they're going to react with that strong base there, right? Now, I do want to pause here in just a second, or for just a minute, and speak outside of an acid-base reaction, because we could get into a situation. Right, if you want to pause here and skip ahead a little bit until I start working on the next problem, that's fine. But I do want to speak here for just a second. Let's say that we had an amide here, right? Let's say that we had an amide instead, right? An NH2 there, right? And then we put in a Grignard. Then the question becomes, well, which carbonyl group is that Grignard going to react with? And there we have to go to our order of reactivity, right? So there we have to remember that acyl groups are more reactive than anhydrides are more reactive than, thioesters and esters and all this kind of stuff, right? So if we're given a choice of which carbonyl groups to react with, then we have to go back and remember, right, which carbon is feeling more positive or which one's more reactive. Okay, and that's a good question, right? It is a good question to remember which carbonyl group is more reactive. And a lot of you guys answered the question in that way, which is, it makes me happy that you guys are thinking about that. But we got to remember if we have a carboxylic acid around there, okay? So I don't want you guys to be too upset with yourself. A lot of you guys answered it with the thought of which carbonyl group is more reactive. So that's just fine, okay? All right, but all that aside, that's not the question that was asked. This is the question that was asked, okay? All right, we're picking back up here in the next set of questions. So now we've got a long string of synthesis here to go through. Okay, so we start with this ketone and aldehyde. We end up making a acetal onto the aldehyde, right? And this is directly from one of the homework problems, or the worksheet problems, I should say, right? So we're putting a protecting group on there. That means we need to add our appropriate group in, right? And we need to add some acid in there, right? P-toluene sulfonic acid is PTSH, right? Or p-toluene sulfonic acid is just, kind of the go-to, but H plus is just fine, right? All right, so under these conditions, we have that diol, we put some acid, we end up reacting the aldehyde and protecting it. Now we come in, right? Next thing that happens is we reduce, right? So we need some kind of reducing agent. So pick your poison is what it is, right? We'll go with some sodium borohydride just because, practically speaking, it's a little bit easier to deal with that guy there, right? So we'll put some sodium borohydride in there to end up reducing our ketone down to a alcohol, right? So now we take this exact guy down here, and now we need to turn our alcohol into a halide. Now, here's where the first kind of tricky question comes in, right? Now, how many ways are there of converting an alcohol into a halide? The answer is quite a few. But there's some specific things we have to pay attention to. First of all, we notice there is no rearrangement. There is no rearrangement of that incoming halide. So that means we can't go through a carbocation, because if we went through a carbocation, we would have to look next door and say, oh, there's a tertiary carbon right there, right? So if we can't go through a carbocation, that means we can't use any acidic conditions, right? Because one thought would be, if we use HBr, will that convert an alcohol into a halide? And the answer is yes, it will. But there's two problems with this. One, it'll go through a carbocation, which will rearrange, and the second is HBr is going to react with our acetal group, right? It's going to react with our acetal group and turn it all the way back into an aldehyde. And that's just not an option for us, right? So be careful about which functional groups you use. So we need to pick a conversion, right? We need to pick some conditions, some reaction conditions to convert an alcohol into a halide without messing with our acetal group there. And there's a couple, right? SOBr2 might be one of them. A better choice might be PBr3, but either one of those, right? So either one of those will get the job done for us, right? Cool. Now, next, we're doing an elimination. We have to take our alkyl halide and eliminate it, right? So put in a strong base. Looks good to me, right? You don't want a super bulky base in there, right? Because we don't want to favor we don't want to favor the elimination to the less substituted side. So we're just being careful about that. Okay, in the next one here, we take we get rid of our protecting group, right? We turn our acetal back into an aldehyde, right? That's just under aqueous acidic conditions, right? H3O plus. Good stuff. And the last is where we take our aldehyde and turn it into an alkene. And here we need our good old friend, Mr. Wittig, right? So we'll set up some Wittig conditions, and that's going to swap aldehyde for a CH2, right? The aldehyde oxygen gets swapped for the CH2 group there. Okay. And then the last one here, we'll say, okay, well, what do we have? Well, we've got a diene, right? We've got a diene, which is somewhat activated, right? We've got these alkyl groups on there. Some of them are somewhat electron donating. And then we've got a alkene that is electron withdrawing, right? With an electron withdrawing group there, a nitro. So we got a diene and a dienophile, right? So this is, and we're heating it up, right? So we got some conditions here for a Diels-Alder, right? So all that shenanigans, right, to do a Diels-Alder reaction, right? And remember, a Diels-Alder reaction, we end up making a 6-membered ring right here, right? Whoops, that should have been in yellow here. Sorry, let me go back and fix that in yellow. Put that in yellow. Okay. And there it is. Okay. So a diene with some donating groups on it and a alkene with withdrawing groups on it. That's set up for a Diels-Alder. Okay. Alrighty. So there it is. There's page 2, and I'll see you in the next video.